This is Group 8 presenting on our analysis and redesign of a coffee bean grinder. Our product is a coffee bean grinder. The beans are first poured into the bean container and a user turns the handle to turn the bean grinder. The grinder position can be controlled to adjust the ground size. The grounds drop down into a collection box below the grinder for the user to access. Our anticipated volume is 200,000 parts per year, over 5 years for 1 million total.
The exploded diagram shows that our coffee bean grinder consists of 22 different components, of which some are used several times. The coffee beans are placed in item 3, the bean container, and are physically ground by components 5 and 6, the outer grinder cup and the inner grinder.
Our primary customers are coffee enthusiasts who care about what goes in their coffee and how it is prepared. They care about great consistency and quality of coffee grounds. It resembles a showpiece that stands out in the kitchen counter. The estimated production volume will be about 80,000 units per year. Our secondary customers are the coffee drinkers looking to reap the benefits of fresher tasting coffee. They're more interested in the function of grinding coffee beans. They're not really concerned about the precision of the coffee grounds. The estimated production volume will be about 120,000 units per year.
The fast diagram shows that our task is to create coffee grounds. To do this, we have to grind beans by first containing the beans and adding energy to grind them. We then must separate the grounds from the beans by dropping the grounds and containing the beans. Our supporting functions are to protect the user during operation of the grinder, allow the user to control the speed of grinding as well as controlling the size of the grounds. Lastly, designing the grinder to allow the user to see both the beans and the grounds adds to the user experience.
Once we define the functions of the product, we generate 2 possible assembly sequences and we evaluate them to select the most appropriate alternative. The main advantage of the first proposal is that it's more oriented to be assembled in a parallel sequence to accelerate the assembly process and to provide more flexibility to different modules. The advantage of the second proposal is that can follow a just-in-time assembly process. Based on their characteristics, we select the first alternative as the preferred one.
This is our bill of materials with our part materials, processes, and part costs. The components are produced from injection molding, die cast, machining, extrusion, and stamping processes. The components with the largest effect on the total unit cost include the inner grinder and the support. The grinder component has detailed features that require careful machining. The support has a more complex shape that will be die cast and have additional machining steps. We assumed a labor rate of $10 per hour with a volume of 1 million when developing this cost data.
This quad chart highlights the items with high importance and high manufacturing costs that will try to be redesigned. The bean container results in high manufacturing costs due to there is no alignment features to the base. The inner grinder is a machine part that involves multiple complex precision milling cuts. The main shaft is extruded but requires several different post-processing operations to create the final part. The support is a large die casting part requiring post-processing machining. Lastly, the 2 gears are both machine parts requiring complex milling cuts. We will try to redesign these parts to reduce the cost of the coffee grinder.
Here is the function component mapping matrix of our coffee bean grinder with the primary assembly components going down the rows and the terminal subfunctions of the fast diagram in the columns. Note how the key functions, namely adding energy and controlling speed, are split up amongst the most critical components. You'll also see that some of the components may have very few or no functions such as the base, slider cover pin, and pivot pin, indicating a potential for redesign. The primary and secondary customer groups require the coffee grinder to have most of the same functions. The critical difference between them is the ability to precisely control grinding speed, which coffee enthusiasts value much more than the average coffee drinker. Likewise, most of the parts are common between the 2 designs. The difference lies in the power input. Either the grinder is cranked by hand, which enables precise speed control, or the shaft is spun directly by a small motor.
Based on the customer expectations and in the functional differences, the 2 modules defined are focused on the energy source and in the way to transfer the movement to the grinder. The manual version consists of 5 components to transmit the customer applied force with precision to the grinder. In the electrical version, there are 4 components and the force is applied by a motor. Both modules will be assembled to the rest of the grinder that is considered as a platform. The grinder support is a component that will provide the access and the attachment point for both modules. The lateral gear have the capability to be connected to either shaft's version. As was stated before, the platform has the majority of the parts and the flexibility to receive both modules without the necessity to modify any component. The platform consists of two sub-assemblies done in parallel. Subsequently, the platform receives the shaft that is attached to the main gear of the grinder and the rest of the components required for each module type. And finally, in the product family assembly diagram, we can identify how does the application of the delay differentiation helps to maintain a single product close to the end of the assembly process. The product differentiation is done in the last quarter of the assembly process.
Thank you.